All right, I'll go blind. Okay. um, I'm gonna start then. Okay, thank you. Uh, thank you over there in Oxford for all your efforts in making this work. I'm really sorry not to be there. So I appreciate for you to make this possible. Um, so in this talk, I'm gonna talk about things we did a couple of years ago, but actually throughout the last couple of years. Following an amazing workshop we did in the US, thanks to the AMS MRC program, mentored by Valeria de Paiva. So thanks for the organizers of MFPS, but also of the MRC, in particular to Valeria, for making this possible. So I'm going to talk about lenses, optics, and morphisms in dialectical categories, which are we could gather them under this vexil of things that describe dialogues. So bidirectional transformations between two sides that are sending back and forth messages. Of course, there's more to each of these things, like lenses have a role in database theory, optics have a role in whatever functional programmers do, and dialectic categories are a whole logical aspect to it. But if we look at what's common, that's what it is. And so the question is that we started with was how they are related. And this is a talk about one possible way to relate them. And I'm not going to talk about references, so I just put them all here. Sorry if I didn't put the references in the right places. But anyway, let's start with vibrations. So this is going to be a talk about how to use vibrations to do cool things. And specific vibrations like the vibration of lenses. So if you have a Cartesian monoidal category C, you can build this vibration of simple lenses. Specifically, you can build a category of simple lenses whose objects are pairs of objects and whose morphisms have this shape here. They're given by one arrow between the bottom object, so U and V, and a morphism like this that we think of it on top. And you can picture this as a dialogue, right? U says something to V, and the V answers a Y and remembers the question that you asked and gives an X back. So you can picture this in the following fashion, right? So that's what I was talking about, top and bottom. So you have here pairs that are represented by projections, and then a lens is given by a map between the bottom things, U and V, and then a map between the top things that go in the other direction, right? And you see this goes from U times Y to X, since it's really trivial on U because of the commutativity of this. And in fact, you can generalize this a bit and say, why just looking at projection morphisms, if you're finitely complete as a category, then we can look at any morphism. And then you still have a map from U to V as morphisms, but now the backwards map is a bit more refined. So the type Y can depend on what F does on U, right? So it depends on V. And this kind of dependency is encoded by a very similar diagram as before, which goes on like this, right? We still have a map here that's on the bottom. Here are the boundaries that are now arbitrary morphisms instead of projections. And then F sharp is now going from the pullback of the second object along F to the first object, okay? And taking this pullback is such that we're now looking at all the possible answers that can be given to the question that the first person asked. Now we can generalize this even further and say, well, let's just look at any vibration P, and then we can build a category of P lenses out of it, where objects are now basically objects of E, which we think of as given by an object in the base U and an object X in the fiber over U. And then morphisms are given by still a map between the base objects in C, and then a map in the fiber that goes from the pullback, which is now given by the fibration structure of y along f to x. And then again, I didn't include that, but this has the same structure as before, right? Instead of taking a pullback as in an actual pullback homomorphism, we're reindexing, we're taking a Cartesian lift, okay? And so in fact, all lenses are P lenses, right? And we just use two particular kinds of fibrations to build the first two examples. So lenses were built out of the simple fibration, which is a fibration whose objects are pairs and whose maps are pairs of morphisms of a certain kind. And dependent lenses are related to the fibration of arrows of a finitely complete category. And then clearly these are examples of P lenses. Specifically, let's see how you build P lenses completely fibrationally. So recall that if you have a Grothendieck fibration from E to C, then this induces a factorization system on E, which is given as follows. So you have phi going like this. So I use this notation to say that X is an object over U in C. And then you can always factor phi as a vertical map, where vertical means that P sends it to an identity, followed by a Cartesian map. And in particular, you can now think also of the maps as pairs, right? So we can think of this factorization system as displaying E as being made of pairs, not just in the objects, but also in the morphisms. So there's a pair, it's a pair of a Cartesian morphism, which is really a morphism in C at this point, and a vertical morphism, which is this F flat. Okay, so we see how this fiber category then gets sort of factored into these two pieces, and that's why it's called a factorization system. Now, if we have a Grothendieck fibration, we can use this to build something called its dual. So ideally, the dual of a vibration is another fibration that it's built by taking the opposite of each of its fibers, okay? So concretely, E dual has the same objects as E, but its morphisms are constructed by formally inverting the vertical part of each morphism. So if before we had these morphisms, now we have these morphisms. So notice how F sharp, now it's a morphism going in the other direction, okay? And so a morphism in E dual is one of these formal spans, okay, given by a vertical map, in P vertical map and a P Cartesian map. And if you squint a bit, you realize this is exactly what a P lens is. So we characterize P lenses in this extremely simple fashion, which is a P lens is just a morphism in the dual fibration, which is really neat. Now, let's look at dialectica morphism. So let's recall what dialectica, the simplest version of a dialectica category is. So if you have C Cartesian, then its objects are triples of two objects in C and a sub-object of their product. Okay, you can think of alpha as a relation or a predicate on the product. And then a morphism is given by triples again of two morphisms in C, which you see are very similar, where I actually form a lens, a simple lens as before. So notice in particular that F sharp goes the other way with respect to F. And then we have this third component, which is a property, if you like, of the morphism. So we are asking that this condition relating the predicates on the boundaries, these alphas and betas, with the F and F sharp, okay? And so we see that in some sense, dialectica is a category of lenses plus this extra level, okay? We also have this other morphism, which is really an implication in this case, or an inclusion of relations, which relates something that happens at both boundaries. And so we like to make this precise. Well, can we construct dialectica as we constructed lenses? And can we abstract that procedure in the same way we did it for p-lenses? Okay, because this is a definition that is very concrete, right? It's just you start with a Cartesian model category and you do these things. Whereas we might try to get a general construction for Dialectica. So let's start by breaking down the pieces. So suppose, as before, we replace the lens part with a p-lens. So that let's say we abstract the first two pieces of the Dialectica morphisms by saying, oh, this comes from a fibration. Okay. Then the predicates, we can think of those as also fibered over E. Okay. So we're really looking at this tower of two fibrations, one on top of each other, right? Where you see that each level provides a new, really going up, each level provides a new piece or a new ingredient in the definition of Dialectica, with the topmost being the predicates. Now, if we try to produce Dialectica by dualizing P, what do we get? Well, first, notice that that tower of fibrations I just showed you can be sort of folded on itself and be considered as really a map of fibrations, right? So this Q can be considered as a map from the composite fibration PQ, QP, and the fibration P, okay? Which in particular testifies that Q respects Cartesian arrows. And then, since taking duals is a functorial construction, this means that we can apply it to this triangle, which is really a morphism of fibrations, and thus we get this new thing. So we have P dual, Q dual, E dual, P dual again. So let's see what we have. So E dual had this factorization system given by formal opposites of verticals and Cartesian arrows, right? Now on P, which is the topmost object, we now have a third, like a more refined factorization system, which is given by Cartesian arrows back to Q, which is the projection of P onto E, which are made of Cartesian arrows and vertical arrows in P, and Q vertical arrows, which are bona fide new maps in the fibers of Q. So in practice, we have a ternary factorization systems on P, so the topmost category, which is given by Q vertical morphisms, P vertical morphisms, P Cartesian morphisms, okay, where these last two are factoring the Q Cartesian maps, okay? So when we do the inversion, okay, when we do the dualization, what happens is that we are dualizing P, right? So the P vertical maps get inverted, and also the Q vertical maps get inverted because we're dualizing the whole topmost layer, right? And so we get this other ternary factorization systems on P dual, which is given by formal opposites of P vertical arrows, formal opposites of Q vertical arrows, and P Cartesian arrows. So this factorization system can be seen as arising from something called an ambifibration structure on Q dual. What is an ambifibration? It's something that is both a fibration and an off-fibration at the same time. So it's a fibration, so it's a functor landing in D, a category with a factorization system. And with respect to arrows in L, the left class, it is an off-fibration. And with respect to arrows in R, it's a fibration. Okay, so it admits co-Cartesian lifts of left arrows and Cartesian lifts of right arrows. Okay, so we can display it like this, right? We have in D, we have arrows which are substantially made of two pieces, a piece in L and a piece in R. And then over it, we can always form this sort of two-sided lift, right? We can, if you give me an A prime and a C prime, I can pull back the C prime along the R map, and I can push forward the A prime along the L map, and then a map in F will be formed by one of these co-Cartesian lifts, followed by a vertical map, and followed by instead a Cartesian lift. So here we have the ternary factorization system, which is directly linked to that of an ambifibration. So So we had this situation here. Where are we now? So we have E dual having the factorization system we've seen before. We have Q dual, which is an ambient vibration on E dual. And then we can look at maps in P dual, as I did in the previous slide, given by this factorization system, which we have now the co-Cartesian maps, which are the Q vertical, sorry, the P Cartesian maps, which are going the opposite way. And then the other two pieces, which are going one way, the other way, okay? So this is almost like a dialectica morphism, right? Because it's made of one piece going forward, one piece going backwards, and one piece going forward again. But it's not, we're not quite there yet, because we need to do another round of dualization. So we introduce this construction, which is basically an extension of the dualization of the taking a dual of a vibration to a whole tower or sequence of vibrations, okay? So suppose you have P, which is given by a sequence of n vibrations, okay? So each of these, it's a vibration on top of the other. And as you may know, the composite of vibration is also a vibration. So this is a vibration in many different ways. And now we can take its iterated dual basically by dualizing each prefix iteratively, okay? So we start by dualizing the first, and we get this. And then if we have a longer sequence, what we do is we dualize the first thing, and then we look at the suffix that remains, and then we dualize that again, okay? So the result is, well, there's an example that's probably not very interesting to look at, right? And then when we are done with this construction, which is turning around all the morphisms one level at a time, the morphisms in the topmost category will be called P dialenses of height n, okay? So let's see in practice what a dialence of height 2 looks like. So we start with E0, the lowermost level. And then, okay, we have a vibration on top of it, so we can consider objects also over U and V. And now to get morphisms in E1, we can say, okay, take F, take its Cartesian lift, pull back Y, and now we have F sharp, which is the vertical part of a morphism in E1, okay? But at this point, we dualize, and so when the dual, in this dual vibration, now the morphisms in E1 are made by one component at the bottom and one at the top that points the other direction. Now we add a new layer, and this new layer is already being dualized, like it's following the dualization at the bottom, but it hasn't been dualized in itself, right? So we have these two alpha and beta here. Now let's make room for describing what's happening at the top with arrows. So an arrow here is going to be made by a Cartesian lift of something in E1, a co-Cartesian lift of something in E1, and a vertical bit, okay? And this vertical bit is now pointing this way, which is the wrong way around, because we have to dualize one more time, okay? So now we're done. We did the whole iterated dual of this tower of two vibrations. And you see we are, like, what we remain with here is the description of a generic morphism in the topmost category here. And this topmost category is made of this interleaving arrows, right? Going and changing directions every time. And so this is why I put this picture here. So it's like we're going up a ladder, and every time we go up, we are changing direction, okay? And this is going to describe something like a dialogue, right? Because every time we do a turn of the dialogue, we change direction of interaction. So let's see how our examples fit into this idea. Well, of course, lenses, or P lenses specifically, are dialenses of height 1, because height 1, the iterated dual, is just a dual, and we've just seen that P lenses are the dual of a vibration. And then dialectic morphisms are dialenses of height 2. And we can see it here. So first of all, we need to construct these two fibrations here, this tower of fibrations. And the way we do that is sort of by reading the definition of dialectica and be like, okay, at the bottommost level, we're going to have objects and morphisms in C, the Cartesian monoidal category we start with. And then what do we have on top? We have the simple fibration, because then we're looking at like simple lenses basically there, right? And so we're looking at pairs of objects and blah, blah, blah. And what's at the third level? So the third level, we have predicates, or let's say sub-objects of the product. So to build this fibration, we pull back the sub-object fibration of C along the, this is a comprehension structure in the simple fibration. So this is sending a pair of objects to their product, and we're pulling it back. So these three, these two, these two fibrations are exactly the data that, when fed to the iterated dual construction, give us a description of dialectica, okay? And this takes a bit to unpack, but if you do it, you realize that this condition here is exactly that condition that you've seen when I gave the definition of dialectica category. And then this gives also like a way to go beyond, so to do something called the dependent dialectica construction, in which we simply replace the simple fibration that we use here with a codomain fibration, okay? And so we also implicitly replace C with a finitely complete category here. And so the bottommost, we only change the bottommost, the lower levels, right? And now instead of a lens at the bottom, we have a dependent lens. But then everything else works the same. So we do this iterated dual, and we get this generalization of the dialectica. And finally, you can show that optics, so in particular, like something related to optics called pre-optics, which, well, if you don't know about optics, then this is not going to be very useful, but it takes too much time to introduce them. If you know about optics, then you know that optics are equivalence classes, can be presented as equivalence classes of some morphisms. And yeah, so the pre-optics are just these optics without the equivalence, really. So sorry, without the quotient. And so we want to avoid quotients here to make this all easier. And likewise, the pair construction is something that takes a category acting on monoidal category acting on another category and builds a bicategory, which here we consider just as one category of morphisms parametrized by that monoidal category acting, okay? So here we have, on the bottom, we have the one object category corresponding to the monoidal category of residuals of the optic. Para is op-fibered over it, which means that if you have a parametric morphism, you can project away the objects and then project the parameter of the morphism below. And then it turns out, again, so this is op-fibered, so you can push a given object along a residual here to get exactly its action, and that's how you see an action of a monoidal category as an op-fibration. And then if you have a different action of the same M, you can build the analogous op-fibration here. Now we pull it back and we get a new op-fibration here. This op-fibration here is the third level. And you can see this third level is now given by maps of this kind, okay? So if you put everything together, the data of something in this, of a morphism in this category here, so we implicitly done the iterated dual, of course. And now we have something there is made of, well, so its objects are pairs of two objects because the bottom objects are trivial. And then together, like a morphism is given by first a choice of residual in M, and then a map from Y to M times X, and this is the forward part of the optic. and the other one goes the other way around. Okay. And so we get something like optics, very close to optics, and this is somehow interesting. So we have, well, Peter Hofstra did some work on the dialectic construction in fibrations, and you can relate our construction to his. As I'm out of time, I'm not going to do that. So just recap what we did. We've seen that lenses can be built by simply dualizing a fibration. We've seen that dialectica categories are a lot like lenses, and we concluded and we've shown that dialectica categories can be constructed as iterated duals of towers of fibrations. So generalizing what we do for lenses, and you can do pretty much the same thing for optics. And that's all for today. Thank you very much. I see Alex is apologizing for the technical problems. No, I'm really appreciative of your effort. Thank you very much. And if there's questions, I don't know if there is time, but maybe you have to type them in the chat because I cannot hear you. Okay, you're muted, so maybe I can hear you. No, I cannot.
Is that any better?
Okay.
Yeah.
I can hear you now, yeah.
Okay. Fantastic.
Yay.
Okay. So,
just in time.
Are there any questions? And I'll hand over the microphone to anyone. Yes.
Hi, Matteo. Great to hear you, to see you.
Hi,
trying
Maria.
to talk about that. I have a quick question for you because Neil Gannett yesterday talked about a specific predicate on lenses. Oh, actually, he was talking about games, and he was trying to talk about equilibrium as a predicate on the games. Do you think the stuff that you're discussing can do with specific predicates that have interest in computing properly?
So I don't know exactly what these predicates for games are. I've neglected that part of the Dialectica project. I'm sorry. But I know for a fact that you can do something like separation logic. I don't want to say anything too wild, but yeah, I guess the point is that if you have specific interesting predicates that you want to put in your boundaries, and then you can ask for the dialectic morphisms to be the way they are so that they preserve those predicates you have. And so that condition looks like a precondition, postcondition thingy. I don't know if I answered your question. I guess you can do that for games.
You can say that.
That's great. Sounds good. We'll try.
Are there any other questions? If there aren't any other questions, we'll thank the speaker.
Thank you.